Okay, so here's this situation that we have. So now we have a finite interval, but close to 2, the rate is, if we approach 2 from the right, so if we approach 2 from the right, the rate of change is getting infinitely large. And at first glance, we might say, look, that quantity can't possibly converge to a finite value. But we saw that when we let the interval run out indefinitely, it's possible, right? So we got kind of the same question here. So will this be, if we accumulate all the quantity at this rate, from this really high rate starting at 2 to 4, will that quantity, that change in the change in total amount, be finite or not? So we do the math. Okay, so we're going to do the math. So if we go, so rather than, if we have that integral from 2 to 4, where's the issue? The issue is at 2. So we're going to do what we did before. We're going to say the limit, now not as a approaches infinity, but as a approaches 2, and then it has to be from, we want to approach 2 from values greater than 2 decreasing. So that's from the right. So we put this little plus here, and that means we're going to look at limits, values of a greater than 2, but getting really, really close to 2. And then we're going to go from a to 4. So we've got this infinite situation at 2. That's where we need a limit, right? So instead of 2, we'll put a, and then we'll take the limit as a gets close to 2, coming from the right side. That's what that little plus means, coming from values greater than 2. Okay, and so then we've got our antiderivative already, right? That was 5/4. See if I can remember. ln of minus or plus? Minus.
Minus.
Thanks. And so we're going to take that from a to 4, and I forgot the limit already. It's the limit as a approaches 2 from the right. So now we're going to evaluate. So we're going to have 5/4 natural log of 2 minus 5/4 natural log of 6. That's plugging in the 4s. And then minus 5/4 natural log of a minus 2, and minus plus 5/4 natural log of a plus 2. And I think, yeah. So as a approaches 2 from the right, here we get 5/4 natural log of 4. No problem, right? So this is fine. This will be, when we evaluate that limit, this will be 5/4 natural log of 4. Evaluating that limit. These don't have anything to do with a, so they just keep their value. So our real question is this bad boy right here. Okay, so as a approaches 2 from the right, so like think of a sequence of numbers 3, 2.5, 2.1, 2.01, 2.001, 2.000, getting closer and closer to 2, coming from values larger than 2. So what will that thing approach? No, a minus 2 will approach what? That is going to approach 0. And so then what happens to the natural log as your argument gets close to 0? Do you know what the natural log graph looks like? Negative infinity. This is natural log. Looks like this, right? So as a gets close to 2, this argument gets close to 0, and natural log of that will then go to negative infinity. So conclusion about this particular, is this amount of change from 2 to 4 at this rate, is it finite or infinite? Or is it convergent or divergent? Divergent. So all these terms are fine. They're all finite values, but this one term just gets really big negative. Okay? And so, but yeah. minus and negative. So basically what we're saying is, in this particular case, this rate getting infinitely large results in an infinitely large change in the quantity or amount of stuff from 2 to 4. Does that make sense? That's what the map told us.
So would we say diverging?
No, just divergent.
Okay.
Oh yeah. Oh, so divergent, and then if you want a positive or negative infinity. So this limit goes to negative infinity, but we're subtracting.
Right.
So this limit is divergent positive infinity. Divergent to positive infinity. Yeah, I think this is web work that asks you to differentiate between negative or positive infinity on the divergent. Right, and it better be positive because this rate is all positive here, between 2 and 4. So the amount of the quantity is going to be a positive amount. That agrees with what we're looking at. Questions on this example? Yeah?
So we were kind of talking about when you're looking at the antiderivative and you have a red flag, we look at the natural log of 2 minus 2. How does that differ from looking at the y and you say 2 squared minus 4 equals 0, you can't divide by 0, but that's a red flag?
But the point is that some of these improper integrals do converge.
Okay.
Yeah, so yeah, you see that you get a 0 in the denominator, and that's where you're that's a warning that you have an improper integral. But that doesn't mean just because we have an improper integral, some of those converge and some of those diverge.
Okay.
So we still have to do the math and show that this one in particular is divergent. But it could have been convergent based on the way that the rate is going to infinity, right? So the way that this rate is going to infinity, it's hovering further away from 2. It hovers far enough away from 2 that our quantity just diverges, gets infinitely big. If that rate function got to 2 quicker, if it got to 2 quicker, then there'd be less of this big rate and it might converge. So that's what we'll look for in a different example. Okay, any more questions on this one? Yeah?
Isn't there like some way to assign a value to these divergent properties?
What do you mean assign a value?
It's like some principle, I think the guy's name.
I guess, are you talking about like a value, a number? Because it just gets infinitely big. Does the quantity, because of this rate getting infinitely large in the way that it does, this quantity is also going to get infinitely large, so it increases without bound. So there is no value. But
Things that like don't exist at that point, something like that.
what's that?
Not for things that like diverge to infinity.
Okay.
But things like
That do converge?
like trigonometry, where as you go towards infinity, it has
Yeah.
a certain value.
Yeah.
So couldn't you use like some principle to find or to assign value, not like the actual answer, but I've like heard of it before. I don't know what it's called.
Yeah, I'm not following. What is it?
I'm not quite sure what you're bringing up, but there are characterizations of infinity. But as far as the purposes of this class goes, we're really just worried about like a 0th order characterization of the integral. Like, tell us what number it converges to, or if it's not a number. That's it. But like mathematicians go crazy on this type of stuff. I'm sure somebody found a way to classify it even further.
Okay, let's try another one. So how about let's do this one from 0 to 1. So I want to do the integral from 0 to 1 dx. Where's the problem here? At 1, right? At 1, we have a 0 in the denominator, right? So let's look at that rate function and see what we're looking at. So here's this rate of change. It's 0 at 0, but then as we get close to 1, it gets infinitely large. So the question is, even though that's getting infinitely large, does our change in the quantity, is it a finite value? Does it converge, right? So we're talking about this integral. Does it converge or not? So we got a antiderivative, which was negative two-thirds.
Square root of 1 minus x cubed.
And now we're going to do the limit of that. So what we need here then is the limit as a approaches what? So it approaches what from what side? 1 from the left. Now, so we want to get close to 1 now, but from the left side, so we're going to do this little minus there. So this is how we're going to rewrite this improper integral. Limit as a approaches 1 from the left, 0 to a. And so then we'll keep that limit notation. Limit as a approaches 1 from the left. And then we're going to go from 0 to a. Now we're going to evaluate at the limits. Negative 2/3, 1 minus a cubed, plus 2/3, sorry, that's an a. 2/3 square root of 1 minus 0. Did I plug things in correctly? All right, so when a gets closer and closer to 1 from values less than 1, we're asking what happens to this. So as a gets closer and closer to 1, so now we're talking about like 0.9, 0.99, 0.999, 0.9999, right? So just getting closer and closer to 1, what is this square root of 1 minus a cubed going to do? You said go to 0. Agree with that? A cubed will get closer and closer to 1 as a gets closer to 1. So 1 minus 1, this will go to 0. And so then what does our limit equal? If this thing goes to 0, then our limit equals 2/3. So here's a case where the rate gets infinitely large as you get close to 1. But despite that, you still have the quantity still grows to a finite amount. Okay? And why is that? It's because the rate, it's like, it gets close to 1 before it gets big, right? So it gets really close to 1 before it gets really big. And it only gets really big when it's really close to 1, and so that's why this thing has a chance to converge. So it's not big for very long, is what I'm saying, right? So it's still pretty low. You know, when you're close to 1, it's still here. It's just a rate of change of 5, and now we're really close to 1, and so it doesn't get really big until really close to 1, and so then it has the idea that it's going to converge.
So it's like the same thing we were doing with like 1 over p, but like rotating.
Right. So it's like now thinking about the other types of improper integrals. We said, did it get down to 0 fast enough? Well, is that rate getting to 1 fast enough so that it's not a really large rate for very much interval of x, right? Okay, let's do one more. So what was the next one? Any questions on this one? Yeah.
Can you go back to the other graph real quick, or is it gone?
I can put it back up there.
Like, just how do you know if it's like fast enough?
Do the math. So we're making.
So like right there, like it's technically like it approaches infinity.
It's because we got a positive value. So we got a finite value. Therefore, we conclude it's not getting big until you're really close to 1. The rate.
When you, like when you said it's basically 0, how can you conclude that it's
Well,
0?
no, that we know. So this is the limit as a approaches 1. So as a gets really, really close to 1, a cubed likewise gets close to 1, and 1 minus 1 is 0.
Okay.
You see that?
Yeah.
So we're just evaluating that limit. Yeah. Okay, let's do another one. Which one should we do? This one? Let's do this one. Okay, so say we want to go this one from 0 to 5 or something. Okay, what's the problem with that? What's the problem with that? Yeah, so at 0, this rate function gets infinitely negative, right? So it gets really big negative. So we're gonna evaluate what the total change in this quantity, whose rate is ln of x radical x from 0 to 5. So we have an issue here at 0, so we need a limit. So we're going to take the limit as a approaches 0 from the right or the left. From the right, so we're going to do the plus, and then we're going to go from a to 5. And now we're going to use our antiderivative that we found. We had to undo the product rule. And tell me again what it was.
2/3 x to the ln of x minus 4 ninths x to the halves.
And so we want the limit as we go from a to 5. And a is approaching 0 from the right. Okay, so we're going to plug our 5 in. So it's going to be the limit as a approaches 0 from the right of 2/3 a to the 3 halves ln of 5 to the 3 halves ln of 5. Good so far. Minus 4 ninths 5 to the 3 halves. No problems there. Okay, and then minus 2/3 a to the 3 halves natural log of a minus, plus, or so that'll be plus 4 ninths a to the 3 halves. Okay, so finite value, no problem. Finite value, no problem. What's this limit? As a approaches 0, of 4 ninths a to the 3 halves? 0. So that's going to go to 0. So here's our question here. So the limit as a approaches 0 from the right, 2/3 a to the 3 halves, natural log of a. So natural log of a gets infinitely large negative, but a to the 3 halves goes to 0. So we have like 0 times infinity, or 0 times negative infinity. So we can rewrite this in order to do L'Hopital's rule, right? So we can do 2/3 natural log of a divided by a to the negative 3 halves, and now we get infinity over, we have the infinity over infinity case, and we can apply L'Hopital's rule. So you can apply L'Hopital's rule when you have infinity over infinity or 0 over 0. And what does it say? It says the ratio of the derivatives has the same limit as this. The ratio of the derivatives has the same limit. So what's the ratio of the derivatives? 1 over a over negative 3 halves a to the negative 5 halves, which all in all becomes 1 over a to the 7 halves. So just forget about the negative 2/3 is going to hold on to. So it's going to be. Did I do that right? Oh no, that's not right.
No, because it'd be negative 3 halves.
Should all be in the numerator.
Yeah,
Yeah.
the 3 halves.
A to the 3 halves in the numerator
And times some constant.
times
negative
negative 2/3.
But that limit.
That's this. No, it doesn't cancel. We're just evaluating this. I shouldn't have carried this down. I shouldn't have carried this down.
Or
We're evaluating this thing that I put in the square, which gives us this negative 3 halves here. So you don't want those to cancel because that was part of L'Hopital's rule, not this. Okay, so we get negative 2/3 a to the 3 halves. As a goes to 0, it does. That goes to 0, right? A to the 3 halves will go to 0 as a goes to 0. So by L'Hopital's rule, this limit is 0 as well. Therefore, that is the change of this quantity from 0 to 5 at a rate function of ln of x squared of x. Whatever that is. 2/3, 5 to 3 halves, all of 5, minus 4/9, 5 to 3 halves.
Can we do that in the graph? Can we just box it?
Sure. Yeah. I'm not interested in you. I know you know how to use a calculator. An answer like this is fine. Okay, so any questions? Do I owe you solutions to the written work? Is that posted yet? I don't think I posted that. I'll post that right now. Solutions to the first 4 assignments. They're all written assignments that I posted on Blackboard, so I'll post those. You've got the review outline and the review sheet. Question?
Yeah, I'm wondering on the test, will we have a graph like this presented or is it
Maybe. But I'm not going to ask you to tell me if it's divergent or convergent by looking at the graph.
No.
Right? It'll always be by doing the math.
Yeah, I was just thinking of whether it's from the right or the left.